It worked. Well, that's a surprise. Well, good morning. John has just given me permission to speak in English, so I will do. And it's from one ex-student of John's to another ex-student. For those of you who don't know me, I'm not sure how many are that do not, but my name's Roger Hoyland, and I did my thesis in, I finished my thesis in the year 2010. It was a thesis, what would you call it? It's not full-time, partial-time thesis, and I did it. John offered to be my external supervisor, and one of the things, just to say this in this conference, when John said he was doing this conference, or when I was told there was this conference celebrating John's work, and I think it was initially about galaxies or the work that John's very much involved in. I said I didn't want to talk because my subject is so different from what John normally does. And John opened up the conference he said, no, I'd like you to talk, and opened up the conference to more subjects. So I've prepared a talk. And just to say that it's taken me back a bit to my thesis, because in that time, my thesis was about a phase switch, basically an electronic phase switch, which was nothing that John was expert in or knew a lot about, and yet he offered to be my external supervisor, which gave me the chance to do the thesis in, I was in the Open University, is where I did my thesis, and he took on the task of being supervisor. So here I'm sort of feeling a bit out of my depth because it's a scientific conference, but John did that for me in my thesis, so here I am. Anyway, the title of my talk is Coherent and Incoherent Receivers in Radio Astronomy. Again, I have to apologize. My background is very much coherent detectors, amplifiers in fact, and my background is the cosmic microwave background. So this talk is going to be very biased, and maybe what you read into what this talk might be, maybe it's not exactly what you think. So anyway, I hope it'll do the subject some justice. Anyway, just a little resume here. We'd just like to go back to the history of coherent and incoherent detectors, where it all started. It's basically been a century, a little bit more than a century of work. Consistent work. There seems to have been continuous updates during that time, and new inventions. And we immediately come across the need, after the initial inventions of these detectors, of the need to cool them. In order to get the sensitivity, there was need of cooling, so it's not just about the detectors, it's about the cooling of the detectors, which was all very important. And so I'll present a little bit about the state of the art. Although the state of the art might be changing, it's changing very fast. There's a lot of work going on these days. We hit fundamental limits, at least by the theory of today, which I'll just pass over. And after the conclusions, there's just a few thoughts I'd like to leave you with for the future. So, this is all from Wikipedia and everything like that. I hope you don't mind. There's no chat GPT. Okay, this is all mine, but it's Wikipedia and stuff. Anyway, coherent detectors. I don't know who exactly to blame for them or who really invented them, but when you look around, there's several names that come up, but the big name that comes up is Jansky, Karl Jansky. He was working for the Bell Laboratories, and it was in 1932 that, as you can see here, this antenna here was what he built. And he basically picked up some static, or what he thought was some static noise in his receiver, which he was making for communications. This is what really drove coherent detectors, was communications, military applications, etc. And so he picked up this static. I believe it was an astronomer of those days said, look, that statics actually coincides with when the galaxy's passing over. And so he started to observe and look at it. He was able to detect a signal at 20.5 megahertz. So one of the things that you can see about the coherent detector, that for me is very low frequency. It's almost DC for me, but maybe it's high for other people. The coherent detectors started off at the low end of frequencies. Okay. If we go to incoherent detectors, well, I think the name bolometer, I think, is the one word that comes out. Again, when we look at who discovered that, there's actually several names that come up. One is William Herschel, who did a lot of work investigating infrared radiation in the 1800s, but apparently he did little there was little astronomical work done on that time. There was Piazzi Smythe, who detected, this is just from Wikipedia, detected the full moon in the infrared in 1856. And then the person we're going to put the blame on, and the person I'm going to go back to, is Samuel Pierpont Langley. And apparently he invented what was then the first time, I think it was called a bolometer. This is a picture of it, this one up here. And my case rests in this poem. I thought it was quite his student wrote a little poem. It was just a little rhyme. So I'll read it to you. It says, Prof. Langley devised the bolometer. It's really a sort of thermometer. It'll detect the heat of a polar bear's feet at a distance of half a kilometer. So with this proof, I'll say that Langley was the one who discovered the bolometers, and therefore incoherent detectors. So if we go along the timeline, which is a little bit what I wanted to present, was the actual development of coherent detectors. This is the sort of thing I've been able to see. So when Langley first used a coherent detector, we're talking about what we have over here, which is the crystal set. It was nothing more than what they call a cat's whisker detector, which was actually one of the first Schottky diodes. Okay, and that is why Schottky diodes are discovered back in the 1900s. They say that was a version of the first Schottky diode, and this was all he had. There was this detector and a pair of sensitive headphones. That's all they had. No computers. No, nothing to look at the data, no graphs or anything. That's what it was. And that's what he was using in his first telescope. As we go on through the 20th century, we start with the valve amplifiers. Some of you may, John will remember valve amplifiers. I do a little bit. I sort of remember some of the in particular, guitar amps have valve amps.
And the radio at home.
A radio. You have one? Yeah?
Yeah.
Yes, exactly. So they were very good, very good. So this was the first amplifiers. And this is the big thing about coherent detectors. There's the way that which we can amplify the signal, the actual signal that's coming in. And as we go through, obviously with the war, the Second World War, etc., there was a big development, a massive development in communications and the drive that brought these amplifiers, that developed these amplifiers until the invention of the transistor, the MOSFETs, these smaller devices, as you can see up here in the 1940s, 1960s. This is when these devices were made and could be used, therefore, in radio astronomy. As we continue on, actually, there was the development of the Josephson junction, superconducting mixers, and we continue on in the 1980s, the development of 3,5 materials, gallium arsenide and indium phosphide, and the ability to make these circuits onto one chip, so that you get so you get multiple elements on one chip, and these amplifiers started to become very sensitive indeed, and the tendency was for the signals that they could actually receive and detect went up in frequency. So we started at 20 megahertz and started to go up in frequency up until today. I mentioned one other thing now, which is something we are actually getting involved in right now, which are system on chips. More and more, we've been able to integrate more and more components onto chips, make them producible in large amounts cheaply. And with this, we have computers today, we have many things. One of the things we actually have are FPGAs, field programmable gate arrays, which we are actually using these days, which are all part of the receiver. And they are actually, they give the receiver some of its properties. So they're all included. If we now go to incoherent detectors, so we started off in the 1880s with the first bolometer. This started to develop through the 20th century until this is more important. It was also the case for coherent detectors, but the importance of cooling these devices to achieve the sensitivity that we need in order to make the detections. And I look at the timeline between 1920s and 1940, the first cooled bolometers were available. They cooled down to 15 Kelvin, I think, in those days. As we moved on, there was the ability to cool down to 4 Kelvin. And this gave rise to devices, superconducting devices. Still bolometers, still, in a sense, just thermometers, detectors of heat, but much more sophisticated. So we had the invention of this spiderweb bolometer. These were on the Planck satellite, and the Kobe bolometers that came before that. So things are still moving on in a very fast and large way in this technology. And more recently, this is beyond 2000, this is just in the more recent years, we're talking now about NKIDs, the kinetic inductance detectors. Again, another superconducting effect, a quantum effect, and TES bolometers, transition edge superconductors. So, this is the development. So, if we're going to talk about coherent and incoherent detectors, we have to talk about cooling systems, because that's the importance. The importance of this is that these devices are cooled in order to reach the sensitivities. Now, there is a difference between the coherent and incoherent detectors, but they both need to be cooled. But the coherent detectors tend to have this sort of gradual increase in sensitivity as you cool them. Apart from cis mixers, which are superconducting devices and have to be below the critical temperature. But certainly HEMS, these high electromobility transistors, and Schottky mixers, they work right up to 300 Kelvin, but they're not very sensitive, so you cool them. In the incoherent detectors, we have the bolometers that work up to 300 Kelvin, but the more you cool them, generally, the more sensitive they become. Apart from NKIDs and TES, which you have to cool down to between 100 and 300 millikelvin. So we are obliged, we have to have these coolers in place. If we're going to make these arrays, very sensitive arrays these days, we need coolers. These days, coolers without microphonics is one of the things that are needed for bolometers and these incoherent. The coherent detectors tend to be a bit more hardy, and you can get away with coolers which are they're pumps, and they're two-stage helium gas pumps. Anyway, both are needed. Both need cooling. So we start to look at the state of the art in coherent and incoherent detectors. This is a fairly old graph, and so it doesn't include everything, but just the general trend you're starting to see here at the lower frequencies, here between 200 and 500 gigahertz. You're starting to see that the coherent detectors are, we've got a double sideband noise temperature here. They are giving the best results, the most sensitive results. And as you go up higher, well, you come to higher in frequency, you get better results from bolometers, high electron bolometers. Okay. So, just to mention one type of coherent detector, which is the low noise amplifier. And in this particular case, the high electron mobility transistors. This one is developed in JPL. It's actually quite recent, but the frequency is 280 to 340 gigahertz. This is, for me, is huge. When I was working on these detectors, they could get up to something like 50 gigahertz. So there's been an improvement, a higher range. Sorry about that. Don't know why that's happened. So there's been an improvement. Basically, the detectors are being used up to higher and higher frequencies. Their noise figure is getting better. Here we are looking at the noise temperature. So these graphs are showing the noise temperature. And also, we have, on this graph, we're showing the quantum limit. And this is where we've got one of the fundamental limits. It's a line where there's, in these detectors, we have quantum noise, which is not the case in incoherent detectors. So yet again, we have another slide showing as we go up in frequency, this is how coherent detectors are, this is their noise temperature and their sensitivity. Obviously it gets worse as we go up to higher frequencies. There are limits, as you can see, the quantum noise. There's two dotted lines behind here which are showing 3 times and 2 times the quantum noise. This obviously gets worse as you go up in frequency. So, the latest developments are with MKIDs and TESS bolometers. Why are they the latest developments? Well, you can build them now on one wafer. You can make thousands of them. They have, this one, the MKIDs have a particularly easy way to read them out. You attach to your MKID, you attach a resonance circuit. That resonance circuit you can see over here in the graph. You can just put thousands of MKIDs onto one line and just read out one line, and you can read these resonance circuits and measure the phase changes. And the phase change in these resonances is proportional to the energy that falls on the detectors, the energy or the temperature. This is also the case with TESS. I haven't got a slide for TESS detectors, but they are starting to use the same technology to read them out, because TESS were a little more difficult to read out. So we look at the graphs here of how things are moving on. You can see as the development here of bolometers, TESS, MKIDs here, generally the noise equivalent power is coming down. Here are some of the latest results here. We're looking at, well, the TESS are giving you the lowest noise temperatures, and MKIDs are sort of there as well. But we also have another slide here, which is about the number of detectors that are possible to be made on one wafer. And as you look here, we have the HEMT amplifiers, or they're fairly low down here because it's actually difficult to make one wafer of amplifiers is not so difficult. One of the reasons is the power consumption. And this moves on. We're getting more and more contribution from NKIDS and tests. Okay. So just a little bit. Am I running out of time?
Yes.
Yes. Okay. Sorry. Coherent versus direct detection. Here we're looking at the quantum limit. Why is there a quantum limit? Well, it's due to the way things are detected. The amplifiers that have this population inversion cause spontaneous emission. And that means that even when there's no energy coming in, you can still get a detection. That goes against it. Okay, with direct detection, it's not that way, that you're just measuring the energy that's coming in. There's another fundamental limit, which is, this is a complicated graph, I won't go into it much, but basically observing from the ground, there's this crossover, and this is another thing between coherent and incoherent detectors. It looks like the incoherent detectors are better at higher frequency, the coherent detectors are better at lower frequency. And depending whether you're observing from the ground, there's a crossover where the best performance is found. If you're observing from space, which you have lower backgrounds, then you are actually better going for incoherent detectors. Okay, just quickly, more recently, we have problems here observing from the ground with all the satellites, the nanosats that have been launched up. We can thank Elon Musk for that and others. And unfortunately, we have to deal with that. For observations from the ground, we have had to change our detectors and the way they actually are built. And we are having to put this system on chips. This is what I was talking about before. We have to put this FPA technology in, technology which takes the signal as is, the coherent signal, and processes it so that we are able to filter out any interference. So, just a very quick talk about coherent and incoherent detectors, which is my field. I'll quickly just go for a thought for the future. There have been a quantum amplifier built. It's a parametric amplifier. This is something for the future. It might be a way in which amplifiers or coherent detectors can get over this quantum limit. This amplifier in particular has passed the quantum limit. I don't know quite how, because I don't know how it works. But things for the future, this might be the way things go. There is another instrument that I came across, which is known as a whispering gallery mode resonator. And this, as the authors claim, works at room temperature. If we could work at room temperature, we could get rid of all the problems with cooling the detectors. Thank you very much.